Swayam Prabha. Digital India. Educated India.
Half wave to single phase cycloconverter. I am going to use a three-phase half-wave rectifier, which is hardly ever used, just for continuity's sake. I am slowly going with, slowly increasing the complexity. So, if I am going to have three-phase input like this, you guys remember the half-wave rectifier for three-phase. We said that for every phase, we have to have one thyristor, right? And then if I connect the load will be connected between this and the neutral. This is the way it is connected, right? This is a half-wave rectifier. We have not included the N converter because this is a P converter. If I may call this as the P converter, I should call this as P1, this is P2, and this is P3. And this is VAN, this is VBN, and this is VCN, with this being the neutral. Obviously, I have to have one more converter with opposite connection of the SCR. So, I can imagine that from all these three terminals, because I am using the same source, I am not going to use a new source. The same source is being used. But I am going to have essentially three thyristors connected in the opposite sense. So this is the second one and this is the third one. Three thyristors are connected in the opposite sense and these are star connected now, and I can connect this to the same point here. You get my point? So if I try to fire P1, P2, P3, I am going to have this as positive. So this is P positive and P negative. Whereas if I try to fire, let me say this is N3, this is N2 and this is N1. So if I try to fire N1, N2, N3, I am rather going to have this as negative. So I should say this is N negative and this is N positive, because it is exactly connected in the opposite sense. But in this case, we will get only half-wave conversion. So if I am trying to draw all the three-phase voltages, for example, so let us say this is, okay, I have to at least draw a couple of cycles, but for which I have not kept space. But I am going to have something like this. So this is the second phase. And this is the third phase. Right? So I have to wait until my other phase, actually that is the P converter current becomes 0. That's what I told you. So if I am actually firing the P converter, I am starting off from here, I may get all these voltage corresponding to P converter. Maybe I will do it until here. So I have given firing pulses only to P1 and P2. And I am not giving the firing pulse to P3. I will wait until the current comes down to 0. Now I can try to give the firing pulse to the next converter, which is the N converter. I am just showing as though I have got only two overlapping half cycles. So I have given this correspond to P1 and this is corresponding to P2. And I have not even given for P3, but I will give for again this corresponds to probably N2, then I will give it to N3 and so on. So I will have again reduction in the frequency, but I have taken as though alpha equal to 0 or even less than that. So I am starting right from the transient condition. Otherwise, alpha should be calculated somewhat like this. That's what we said. So we are looking at the whole thing as though we have to fire the P converter such that ultimately the current will come down to 0. If you keep on giving firing pulses, the current will never come down to 0. So you will not be able to go to negative half cycle at all. So once you hold off the firing pulses to the P converter, you should wait until the current comes down to 0. So it's very important in a cycloconverter to sense the current. Without current sensing, you cannot release the firing pulses to the other set of converter. Otherwise, you will have a dead short circuit. You will have a big problem with the, the connection of the two converters, because you are trying to connect completely opposite polarity together. That's the reason. So this is typically a 3-phase to single-phase cycloconverter, where I have 3-phase supply in the input, whereas the output is single-phase. And it is not sinusoidal. It is still not sinusoidal. Right? Now if I want 3-phase to 3-phase, for example, or let's say first of all single-phase to 3-phase cycloconverter. How do we really connect single-phase to 3-phase? I have 3 different loads, clearly. Right? R phase, Y phase and B phase, because at the output I am going to have 3-phase. But what I have in the input side is single phase. So I have to have for each of the phases one P converter and one N converter. Each of the phases should have independently one P converter and one N converter. So if I have 3 phases, I will have 3 P converters, 3 N converters. So I will have 8 multiplied by 3, which will be 24 devices. Cycloconverter uses really large number of devices. So let us try to draw for single phase to 3-phase. Right? So I am going to have this as my power supply, which is common for all the converters. So I am essentially going to show it in the form of, let us say, simply let me show it like this. This is the P converter. Okay? And let me show the other one either here or I can show it here as well. So I am going to have the other one as the N converter. Right? I had to show similarly 2 more things. So this is A phase or red phase. Then I am going to have one more yellow phase, or let me say this. So I am going to have one more set of P converter and N converter. And I will have one more set of P converter and N converter. So I have got each of them having 4 devices. There are 6 such things, so 24 devices. Now I will connect this first of all to this. Now the output is connected to a load. Right? And normally I am going to have plus here and minus here if it is working as a rectifier. The same thing when this is working as a rectifier, I am going to have plus here and minus here. But this plus has to be connected here and this minus has to be connected here. The other way around, like a dual converter. Right? So I have connected just the opposite polarity. So this is A phase load. Okay? And this is P converter A phase. This is N converter A phase. Okay? Now from here I am going to connect this to this. From here I am going to connect this to this. Same single phase supply goes everywhere. I am not having any more supplies. I have only one single phase supply. It is going here. Okay? So if I may call this as 1 and 2, these are the input sides of the rather, I can say line and neutral otherwise. This is line and this is neutral. So between line and neutral, all the converters are connected. Now I'm going to have similarly, this is P converter B phase and this is N converter B phase. And this is going to be P converter C phase and this is going to be N converter C phase. Okay? Now the input is very simple. I'm going to connect it the same way. So from here again I will take it up, I'll connect it here, and from here I will take it up, I'll connect it here. From here I will connect it. So all of them are connected to the same input. The input is essentially the same. So I have to again show from here, from the same point, I can connect it to this and I can connect it. So I have to take it here. So I have taken it here. So the same thing I can connect it here. All the inputs I have to connect, but when I give the firing pulses I have to make sure that I give the firing pulses always to 1 and 4 together and 2 and 3 together as far as every converter is concerned. And if 1 and 4 are conducting during positive half cycle, I better connect them in such a way that they will conduct during positive half cycle of the input supply voltage. These things I have to take care. So when you make a cycloconverter circuit diagram, if at all you do that in PSIM, there is a demo available also for cycloconverter. You should see how it is connected together. So this is how it is connected. Now I have to again connect a load. So maybe I just take a load like this. This is connected here, this is connected here, this is B phase load. Right? So this is ZB. Let me show this as ZB, that is B phase load. This is positive and this is negative for this converter. And as far as this is concerned, here is going to be positive and this is going to be negative. So this positive should be connected to negative and vice versa. The other way round. Right? Same thing is true for this particular case. Again, I am going to have here this as ZC. Right? So I will have this as positive and this as negative. Here I am going to have this as positive and this as negative. So this positive will be connected here and this negative will be connected here. So that the current flows in the opposite direction. When it is rectifying, P converter is rectifying, I will have the current in this direction. When N converter is rectifying, I have the current in the opposite direction. That's all that it is facilitating. Right? You are going to exactly have dual converter kind of connection. So, if I have made a connection like this, how will I make sure really that I am going to have, the A, B and C phase supplies 120 degrees away from each other. They have to be 120 degrees away. So normally when I try to do single phase to 3 phase, I would like to have 3 half cycles or 6 half cycles or 9 half cycles. So that if I have 3 half cycles of, the input coming up at the A phase, then from the second half cycle or third half cycle onwards, my B phase can start. You get my point. If I am going to have my A phase output somewhat like this, and then it is going to have 3 half cycles like this. This is A phase, ZA voltage, VZA. VZB can be from this half cycle it can start. You get my point, because this entire thing corresponds to 180 degrees. What I want is 120 degree shift. So 2 half cycles will correspond to 120 degree shift as far as the output is concerned. You get my point. So I would have essentially these 2, 3 coming up as the half cycle here, and these 2 will come like this and so on. So this will be ZB. VZC obviously has to start from here. Right? They have to essentially be shifted by 120 degrees of the output wave. Output wave. You get my point? So, I am going to have essentially these going as positive half cycle. So, I will have essentially negative half cycle coming up like this here. 3 half cycles like that. Right? So, this will ensure that I get exactly 120 degree phase shift between A phase, B phase and C phase respectively. So far whatever we have talked about, we are not having any voltage control. Ideally what I would like to have as the waveform is somewhat like this. It should be sinusoidal. This is what I would like to have. And in the other side also I should have sinusoidal voltage like this. Ideally this is what I would have liked to have. Right? Because most of my loads will accept only sinusoidal output voltage. They will not accept non-sinusoidal output voltages. What I am getting is definitely non-sinusoidal. I hope you understand. Because 3 Vm by pi, whatever we are getting, 3 Vm by pi cos alpha, that is the value I am getting if I am firing it at a particular alpha. Continuously. So it is as good as having a square wave voltage. On an average basis, if I try to look at it, it will look as though if I look at the average value, I will have a square wave like this and then I will have a square wave like this. This value may correspond to 3 Vm by pi cos alpha. This is how it is. It is somewhat like this. And definitely I do not want that, especially if I am trying to apply this to a synchronous motor drive or induction motor drive. Cycloconverters are generally used with synchronous motor drives in a big way, because synchronous motor drives normally are of megawatt level rating, very, very large capacity most of the times. And synchronous motor drives generally, because they are of large rating, they will also have a huge inertia, very large inertia. If they have a large inertia, it is going to take a while for them to vary their speed. J d omega by dt equal to Te minus TL. That is the equation F equal to ma. Something similar to that. That's what I'm talking about. So you are going to see that it takes a while before the speed changes even a little bit. So the response time is really, really large for a synchronous motor drive, which corresponds to megawatt level rating. SCR is also slow and they can handle very large power. So they all match very nicely. Thyristor based any converter will work slowly. They are much slower than IGBT or MOSFET or any of them. And they can handle single-handedly almost 30 megawatts of power without any difficulty. Because of which, you know, for high power drives, we generally tend to prefer thyristors. And cycloconverters reduce the frequency. Most of the times, synchronous machines may be run at slow speeds. For some kind of, cement mill where you are trying to grind, limestone and so on and so forth, all those things work very slowly. It is inching. Most of the motor drives will be inching slowly. So in those cases, these can come in handy. From 50 hertz, you may come down to 10 hertz or 5 hertz. So in those cases, cycloconverters come in handy. So motor drives will not accept generally anything other than sinusoid. So how am I going to really get a sinusoid? That's what we'll have to think about. So if, let us say, my output wave is having maybe 5 or 6 half cycles like this. In fact, if I am going to say 50 hertz to 10 hertz, I will have 5 half cycles in the positive and 5 half cycles in the negative. If I am coming down to 5 hertz, I will have 10 half cycles in the positive, 10 half cycles in the negative. So I may have something like this continuously coming up. Right? So this is the way it is going to be. I can approximate this to a sinusoid, provided my average voltage is really small here somewhat larger here, somewhat further larger here, then again it comes down here, comes down further here. I can do that. I can always control my firing angle in such a way that first half cycle I have it close to 90 degrees so that the voltage is very, very small. The next half cycle I can make it 60. The next half cycle I can make it 30 or even less. Then the next half cycle I can again make it, 60. Then the next half cycle I can make it, close to 90. So this will essentially approximate my output voltage to something like this. It is starting from very minimal value, it is reaching a peak here, and then it is coming down to small value. So the control for cycloconverter is not very simple because it is a continuously varying firing angle. I will be definitely varying the firing angle, but if it is an RL load like a synchronous motor, I will have to take into account definitely there will be some negative portion of the voltage coming up. That's the reason I told you that for 90 degrees output is 0. Only if it is continuous conduction. So I need to know what kind of load I am connecting to, and accordingly I have to calculate what is the kind of firing angle I have to give such that my output voltage approximates to a sinusoid. So it is the same thing I will be doing in the negative half cycle as well. So I may get only small voltage, this is a little larger, this is much larger, and then I am going to get, smaller and smaller voltages. Get my point? So this is also going to approximate this entire thing to, a sinusoid somewhat like this. So I can control the output voltage approximately to a sinusoid. It is not a perfect sinusoid. It is only an approximation to a sinusoid. So I am calculating the area under the curve, which is actually 3 Vm by pi cos alpha normally, and then correspondingly I am trying to look at not 3 Vm, 2 Vm by pi for single phase. We are talking still about single phase. So I have to calculate for that and then make sure that the firing angle is adjusted accordingly. That will make sure that what I apply as the voltage is somewhat sinusoidal. And the same thing has to be replicated for B phase shifted by 120 degrees. And the same thing has to be again duplicated for C phase, again shifted another 120 degrees. So this control is definitely not simple, but especially when there were no other devices other than thyristors. That was in 1970s. This was really leading, it was ruling the rooster for as far as the synchronous motor drive control was concerned. Even now many of those drives are there in many of the power stations which are working quite well. NTPC power stations, many of them use cycloconverter fed synchronous motor drive for many of the controls, and they are still working well, so nobody has tried to retire them. They are still working very much fine. That's not a problem. Now actually with the advent of wind energy conversion system, these things are coming back somewhat, because as far as wind energy conversion system is concerned, we will have a variable frequency of output from any of the AC generator. If I have an AC generator, it will be rotated by a wind turbine, and the wind turbine is definitely going to have a variable velocity. It's not going to have a constant velocity. If it has a variable velocity, the output what I am getting from my, the generator, that is going to be at a different frequency. If I want to feed it to the grid, I have to ultimately convert that into 50 Hertz. If I have to do that, normally what we do as of today is to first of all rectify the AC voltage into DC, and the DC is again converted back into AC with the inverter. So you have two stages of conversion, because of which there are many losses. and huge amount of complex control. I'm not saying cycloconverter is a simple control, but this is one stage of conversion. Directly you are converting from AC to AC. But the question is whether we can convert from a variable frequency always back to 50 Hertz. So for that there are several control methodologies that have evolved. So cycloconverter is again having a rebirth. Although it had become obsolete, now people are looking at it with a renewed vigor because it can be used basically for the control of wind energy conversion system from variable frequency output to a constant 50 Hertz output which can be fed to the grid. Right? So much so for the voltage control. I am not getting into great details of cycloconverter because this is really not taught by many of the power electronics teachers. But I thought because it is reviving, at least you should know what is a cycloconverter. That's the reason. Okay? Let us try to take a look at 3-phase to 3-phase cycloconverter. If I want 3-phase half wave to 3-phase ultimately the output cycloconverter, half wave requires 3 devices. 3-phase half wave requires 3 devices. P converter will require 3 devices. N converter will require 3 devices. So 6 devices per phase. And I want 3 phases at the output. Right? So which means 18 devices minimum I'll require if I want 3-phase half wave. If I talk about half wave, right? I will require every phase will have 1 P converter and 1 N converter. And P converter will require 3 devices, N converter will require another 3 devices. So I will require 6 devices per phase. So I will require 18 devices if I am talking about half wave. If I talk about full wave, I have to double it. I will require 36.